So first, looking at your practice worksheet from homework, flip it over to the side that says orbital notation, and it should look at the top something like what I have on the screen here. So you should have the elements hydrogen through neon and several blanks in a table on the right side showing you the different spaces that you can draw electrons, which is what we're going to learn how to do right now. So the first thing I'd like you to do is actually to pause the video, and I've already got hydrogen's electron configuration written here for you, but I would like you to next fill in all of the other longhand configurations for hydrogen through neon. So please pause now, fill those in, and I'll wait. Okay, so this is what your electron configuration should look like. Notice each time we're simply adding one electron to each thing. So down here for neon, we have a total of 10 electrons, which matches its atomic number of 10. Okay, so what we're going to learn how to do now is to show how the electrons are arranged in the electron cloud within their sublevels by using these things called orbital diagrams. So the first thing I'd like you to note is that the number of squares corresponds to the number of orbitals per shape sublevel. So because these are both S-shaped sublevels, spheres only have one orientation, so they only have one orbital within each one. So that's why there's only one square, and that's why you only have one blank on your sheet. Over here for a P sublevel for 2P, which corresponds to this row on the periodic table, that one has 3 squares because there are 3 orbitals per P sublevel. Remember, that's because you can look at a pair of spheres in the X, Y, and Z axis. Okay, so what we're going to do is we're going to add arrows, or half arrows actually, that are going to show the orientation of electrons within these different squares. So that being said, the way we show them is going to be in similar but opposite directions. So for example, because we have a configuration of 1s1, there's only one electron in that particular orbital. So we're going to show it as one half arrow pointing up. Okay, technically it could point down, that's fine, but we're going to leave it that way. Okay, so our next one is 1s2, and we're going to show that one as one half arrow pointing up and a half arrow pointing down because we have 2 electrons in, as indicated by your superscript, 2 electrons within the 1s sublevel. Okay, so we have 1s and we have 2 electrons, 2 arrows. All right, moving along, we're going to have 1s2, 2s1, 1s2, 2s2. Okay, so now it starts to get a little bit different because now we're starting to go into the P sublevels. Okay, so for 2p1, we're just going to draw one electron in the first square. All right, now when we get to carbon, the beginning is still the same, 1s2, 2s2, but now we have 2p2. Okay, and the way we're going to do that is similarly to how we've done electron dot diagrams or Lewis dot diagrams, where you go around once before you go around the second time. So we're going to add an electron to each orbital before we would ever add a second electron to that orbital. Okay, and so this is going to be basically applying Hund's rule. Okay, so if we keep going with that, that means nitrogen is going to have the first 2 squares like that, but then you'll have 3 unpaired electrons here. Okay? All right, so I'd like you guys to finish those out with me. So we're just going to add for oxygen. Similar idea, add 3 electrons to the lonely boxes before we add now that 4th p electron. Okay, so for fluorine, we'll only have 1 lonely electron. I'd still always practice it by doing 1, 2, 3, and then the upside down 4 and 5. And neon is going to be totally filled in. Okay, something I'd like to go ahead and show you right this second is how this relates to what you already know about valence for different elements. So when we would draw nitrogen, remember we'd always draw it with its 5 valence electrons, 1, 2, 3, 4, and 5. Notice this corresponds to our electron configuration. So our lone pair is actually evidenced by these 2 s electrons, and our 3 lone electrons that are available for bonding are the 3 unpaired electrons in the 2p sublevel. So once again, what we're doing with electron configuration is essentially proving all the things that we've already learned. Okay, the same thing is true with checking your work here. So just make sure you have the correct number of arrows that corresponds to the atomic number of the element. So for example, here for oxygen, we know that we should have an atomic number of 8. So you'd have 2 plus 2 plus 4 gives you 8, and you have 2 plus 2 plus 4 electrons in your orbital diagrams, and that gives you 8 as well. Okay, so essentially this is how you do electron diagrams. The last thing I wanted to point out is how all of our different rules apply. So first of all, the order that you're writing the configurations in and the order that you are drawing out the electrons, that is following the Aufbau principle, showing electrons in order of increasing energy. By having your electrons in one orbital before you add a second electron to that same orbital, that is obeying Hund's rule, and the fact that you have your electrons or your arrows showing in opposite directions, that satisfies the Pauli exclusion principle because you are showing that the electrons have equal and opposite spin within the one orbital. So that's essentially how you draw an orbital diagram. The next video is going to be about exceptions to what we learned with respect to ions and with respect to a couple of special transition metals.